So far in this lecture series of DBMS, we have discussed first, second and third normal form, right? What is the basic idea of those normal forms, means what are the rules and regulations for a relation to be in first, second and third normal form, right? And we have also discussed that this type of relation would be given, functional dependencies would be given, and you have to identify that the particular given relation is in you can say in first, second or third normal form or not, right, using those rules. We haven't discussed that if a relation is not in second normal form, then how to convert it into second normal form, means how to decompose that relation. Fine. First of all, we will discuss the basic idea of all the normal forms. So in this video, I will discuss what is BCNF. Now, what are the drawbacks in the second normal form, and because of those drawbacks, the concept of third normal form came into picture. That also we have discussed in the previous video, right? But still, we have some drawbacks in third normal form at sometimes. See, I have told you in the previous video that if your database design, your relational schema is in third NF, then you can say that it is a good database design, right? But sometimes, still because at some cases still there are some redundancy. If your table is in third normal form, but still there is some redundancy exists in that table, and because of that you can get some anomalies, right? When this type of problem comes, because third NF is not able to handle the cases when you have multiple candidate keys and all the candidate keys are overlapping, or you can say we have multiple overlapping candidate keys like this. Suppose in a relation we have one candidate key is AB, second is BC, next you can say DC, like this. See, this and this is overlapping candidate keys, here also C, here also C, here B, here we have B. So when these kind of cases exist, then third normal form cannot handle these type of cases, right? To handle these type of cases, we have BCNF. We cannot say that it is fourth normal form, right? It is, you can say that, a stronger version of third normal form, or you can say advanced version of 3NF. And why it is known as Boyce Codd normal form? Because it was developed by EF Codd and Raymond F. Boyce. That is why it is known as Boyce Codd normal form. It is not fourth normal form, right? Remaining first, second and third normal form was developed by EF Codd only. See, he is known as father of DBMS, right? Now, why this is more strict than third normal form? Let us discuss that. What are the rules for a relation? What are the requirements for a relation to be in BCNF? And after that, we will discuss with the help of 2 or 3 examples that this type of question would be given, and you have to tell this as in BCNF or not. And we will also see with one example that you have to tell the highest normal form exists in that relation, whether it's second, third or BCNF, right? And after this video, we will discuss what is decomposition, and after that we will discuss if a particular relation is not in a desired normal form, then how to decompose that relation, how to convert that relation into desired normal form. So, the rules are, you can say a relation is in BCNF if and only first one is it is in third NF, right? Second rule is for each non-trivial functional dependency. See, I am talking about non-trivial functional dependency, not trivial, right? In the third normal form also we have discussed the rules on non-trivial functional dependency, right? And by default we assume that all the this relation given is in first normal form, plus these dependencies given are in, you can say are non-trivial, because we usually take those kind of dependencies that are non-trivial, right? So second rule is for each non-trivial functional dependency, the left hand side of the dependency must be super key, or you can say the determinant must be super key. Let me write down these rules. So these are 2 rules. It is in third NF. Second is this one. For each non-trivial functional dependency, I have discussed what is trivial, what is non-trivial functional dependency. Suppose functional dependency is x to y, right? Then x, the left hand side of the dependency must be super key. So it is very easy to check if a particular relation is in BCNF or not. Just you have to find out the super keys, or if you don't want to find out all the super keys, then you can go for each dependency and you can check A is super key or not, B is super key or not, and C is super key or not. And how to check that particular attribute or particular key is a super key or not? Just find out the closure, attribute closure, and if attribute closure contains all the attributes of a given relation, then that is what a super key, right? So let's check this relation is in BCNF or not. Fine, see. So here I will not simply check that this is super key or not, this is super key or not, or this is super key or not, because obviously they will give you these type of questions in GATE and NET. They will give you a particular relation, functional dependency, and they will ask the highest normal form exists in this relation. So for that, obviously you need to check for third also and second also, and for those normal forms you need to find out the candidate keys. So let's find out the candidate keys first of all. After that we will check how to find out candidate keys. See, take the all attributes, take the closure, and definitely that would find out all the attribute of the relation. So you can say that this is a super key. Now find out candidate keys. You discard as many elements, as many attributes as you can, because candidate key is what? A minimal super key. Check out the functional dependencies. How to discard? Check out functional dependencies. See, A determine B. It means I have A, so I can discard B, because using A I can determine A, and as well as if you have A you can determine B, right? And it will determine C. It is still having all the attributes. So this is what still a super key. Now can you discard anything else? A determine B, B determine C. It means A will determine C by transitivity property, so you can discard C. So here I am left with only A. Now A is what? Super key. Obviously we are not going to discard anything else because it is single attribute. Single attribute, this will attribute closure will contain all the attributes, so it is super key. Now check it as candidate key or not. Definitely it would be candidate key. Why? Because it is containing a single attribute and no proper subset would be possible. If no proper subset is possible, then there is no chance that the proper subset of this would be a super key. So that is why it is a candidate key. So if A is candidate key, then prime attributes we got A. Now how to check that still more candidate keys are present in this relation or not? If prime attributes are present on the right hand side of any functional dependency, I have already discussed this trick in the previous video. You can check out that video in the side button. Then there would be more candidate keys. So check out, prime attribute is A present on the right hand side of any functional dependency? Yes, here. So you can replace this A with C in candidate key. Candidate key is A, so you can replace it with C. But we cannot say that still it is a candidate key. You have to find it out. It is super key, that thing I can definitely see. Now how to check proper subset of C is possible? No. So if no proper subset is there, then definitely that would be candidate key. So we got two candidate key, A and C. Prime attribute A and C. Check again, C is now prime attribute. Now C is present on the right hand side of this functional dependency. So you can replace this C with B. I am replacing this with B. Now B is super key. Find out it is candidate key or not. Yes, single attribute. Yes, definitely that would be candidate key. Prime attribute is B. Now you can say B is present on the right hand side of this. So you replace this B with A, but we have already checked A is candidate key, right? So now we have got all the candidate keys, that is one is A, B and C. Prime attribute are A, B and C, right? See, all the attributes are prime attributes. Now you check this as in BCNF or not. Now check for each dependency. See, first of all it is in third NF. It should be in third NF. So this is in third NF. I have taken this kind of example that it is already in third NF, right? And if you want to check, then you can check there would be no transitive dependency because all the attributes are prime attributes. And transitive dependency is what? Non-prime attribute determining non-prime attribute, right? Or in another words you can say, first either left hand side is super key or right hand side is prime attribute, right? If any of these two condition holds for each functional dependency, you can say that there is no transitive dependency and that relation is in third NF, right? Now there would be no non-prime attribute because all are prime, so that would definitely be in third NF. Check for BCNF. This is true. Now for each non-trivial functional dependency, these three are non-trivial functional dependency, X must be super key. Check this left hand side must be super key. Is A super key? Yes. So first is what? According to first, it is in BCNF. Now check, this is violating the rule of BCNF or not. Is B super key? Yes. B is candidate key, definitely it would be super key. Yes. Is C super key? C is candidate key, definitely it is a super key. So yes, means each functional dependency is satisfying the requirement of BCNF, right? So you can say that this relation is in BCNF. See why we are saying that it is more strict than third NF, because in third NF we have what rules? Either left hand side is super key or right hand side is prime attribute, then fine, that would be in third NF, right? But here definitely the left hand side, you can say the left hand side must be super key, right? No other condition is there, this must be satisfied. So that is why we are saying that it is a you can say more strict version of 3NF, because 3NF doesn't deal these kind of condition, like if a non-prime attribute is determining a prime attribute, then according to third NF it is not a transitive dependency. Why so? Because right hand side is prime attribute, so it is not going to deal these kind of cases. A non-prime attribute is determining a prime attribute, because of this dependency there would be some problem, right? But here in this case this left hand side must be super key, but here it is not a super key, so it will not allow these kind of dependency here, right? And what about second normal form? This will this second normal form deal with these type of cases, right? If prime attribute is determining a non-prime attribute. See, prime attribute means it should be a proper subset of candidate key. It's not like that it is a proper candidate key. It should be a proper subset of candidate key. Then it will violate the condition of second NF, right? So now you have the idea of all the normal forms, first, second, third BCNF. Now I'll discuss with one example, and I'll give you one example and we will discuss that what is the highest normal form given in that relation, right? See, let us take this example and find out the highest normal form of this relation. See, so for this, first of all we need to find out the candidate keys, all the candidate keys. How to find out candidate keys? First of all, take all the attributes of this relation. Closure obviously will contain all the attributes, so this is super key. Now try to discard. A is determining B, C, D, E, so I have A, so using A I can determine A itself plus B, C, D, E using this dependency. So A attribute closure of A will contain all the attributes of the relation, so A is definitely a super key. Now A is super key, I cannot discard anything else because it is now a single attribute, right? Now definitely that would be a candidate key. So now candidate keys are, first of all, A, we got one candidate key. Prime attribute we got A, the part of candidate key, those attributes which are part of candidate key are known as prime attribute. Now check, is A, this prime attribute present on the right hand side of any functional dependency? If yes, then there would be more candidate keys. Here we have A. See, this dependency can be splitted into BC determine A, BC determine C, BC determine E because of that splitting property. So BC determine A, right? Right hand side we have A. So at the place of A in the existing candidate key, I can replace it with BC, right? BC at the place of A. But BC we cannot say that still as candidate key. You need to check out. Now B is proper subset and C is proper subset. Find out the attribute closure of B and C. Is B determining all the attribute? B is determining B, nothing else, because here both BC will determine AC, but we have only B. C is determining only C, nothing else. So this is not super key, this is not super key. So definitely BC is what? Candidate key. Now prime attribute are, one is B, one is C. Now check out, B and C are prime attribute, those are present on the right hand side of any this dependency or not? Yes, here we have C, right? But definitely we will replace the C. This is what a trivial functional dependency. So if you replace the C with BC, then that would be same, right? Here we have C. This can be splitted. A will determine B, A will determine C, A will determine D, A will determine E. 4 dependencies, right? By splitting property. Now at the place of B, 2 cases can be there. At the place of B, I am replacing A. So first one AC. Now at the place of C, I am replacing A. So second one is BA. These are super keys, but I cannot say that these are candidate keys. Check out. These cannot be candidate keys. Why? So because proper subset of this and this is what? A, and A itself is a super key. So this cannot be candidate key, this cannot be candidate key, right? So in this case, we have only 2 candidate keys, A and BC. 3 prime attributes are there. Non-prime attributes are D and E. Now check. First of all we will check for the highest normal form, that is for BCNF, right? It's better to check for the highest normal form rather than starting from the lowest normal form, right? If these type of questions are given. So for each functional dependency, we will check the rules. First one is this one. A is super key or not? because this is the main condition, right? A is super key, yes, so this is satisfying the BCNF property. BC is super key, yes, because BC is candidate key, definitely it is a super key. Is D a super key? No, even D is not a prime attribute, and if still you want to check, then you can find out the D closer. If D closer contains all the attributes, then that would be super key, but D closer contains only D and E. Nothing else we can derive by D and E. So this is not a super key. So this, because of this property is violating the BCNF rules. So this is not in BCNF. Now find out third NF. See, if this functional dependency is satisfying the BCNF property, definitely it would be third NF and third NF, no need to check, right? Because for BCNF, that dependency should be in third NF, right? So that is for sure that these and these would satisfy third NF rules. You just need to check out this one for this one. D to E. Is this transitive dependency or not? Because third NF we will check, in third NF we will check transitive dependency. Means in that case, check out left hand side is what? It's super key? No. You cannot say that this is violating third NF. Or right hand side is prime attribute. Two condition, at least one should be satisfied, not both. So is E prime attribute? No. So now you can say that this is not satisfying third NF property. Or in another term you can say NPA determines NPA, non-prime attribute. D is non-prime attribute? Yes. E is non-prime attribute? Yes. So this is transitive dependency. So this is not satisfying the property of third NF. Now check for second NF. Partial dependency. So this is in third, so definitely in second, definitely it would be in second. Check out for this one, right? If you are not satisfied with this answer that this would be definitely in second NF, then you can check, right? You will find out that this and this are in second NF. Check out for this one. Second NF, we will check for partial dependency. If partial dependency is there, it is not satisfying that property, right? If this is partial dependency, then that is not in second NF. Partial dependency is what? Proper subset of candidate key will determine non-prime attribute, right? Now, is D proper subset of candidate key? Candidate key are A and BC. Proper subset is, obviously there is no proper subset of A, proper subset of BC is B and C. D is not a proper subset of any candidate key. So no need to check the right hand side, right? Because left hand side should be proper subset of candidate key, right? So this is not proper subset of candidate key. So you can say that this is not partial dependency. If it is not partial dependency, then you can say that it is in second normal form. I hope you are getting my point, right? For this video, you must check out the first, second, third normal form videos. So you can check out those videos in the description box. I'll provide you the complete, link of that complete playlist of DBMS in description box. So you can see that now the highest normal form of this relation is second NF, right? Let's take one more example. So let's take this example and check out the highest normal form in this relation. For that, you need to find out the candidate keys. How to find out candidate keys? Take all the attribute of the relation. Definitely the closure would contain all the attributes. So this is what super key. Now try to discard attributes. How to discard? Check the functional dependency. AB will determine CD. So I have AB, so I can discard CD. D determine A, but I don't have D, so I cannot discard anything. So I have now AB. AB is super key. If you still want to find out, you can find out AB closer. AB closer will have AB reflexivity property, and if you have AB, then you can determine CDE. So it is having all the attributes. So AB is what? Super key. Now is it candidate key or not? Find out the proper subset. One is A, one is B. Closure of A is A only, closure of B is B only. So it is not super key, it is not super key. So you can say that now AB is candidate key, because no proper subset is super key. No, AB is candidate key. We got one candidate key, right? So now we got prime attributes, that is A and B. Now check out prime attributes are present on the right hand side of any functional dependency or not. Yes, here we have A. So now at the place of A in the existing candidate key, I can replace D. So now I got D, B. But I cannot say that it is candidate key. You have to find it out. But I can say that it is super key. So how to find it out? The closure of it is, sorry, this proper subset is D, one is B. Find out closure of D, closure of B. But already we have found out B is not super key. Now closure of D, using D I can find out D and A. nothing else. So it is also not super key. So now you can say that BD is also a candidate key. So now prime attribute is what? D. One more prime attribute we got, that is D. Find out, see here we have prime attribute D. D is present on the right hand side of this dependency, right? By splitting I can say that AB determine D, only D, only C, only E. So at the place of D I can replace it with AB. So if you replace it with AB, then we have already discussed that AB is a candidate key, no need to replace, right? So now no more candidate keys are there, two candidate keys are there, AB and BD. Now find out. First of all, we will check for highest, that is BCNF. Is it in BCNF or not? For each functional dependency, check out the rules. For BCNF, definitely, obviously we will check that condition that the left hand side must be super key. Left hand side of this dependency is AB. Is AB super key? AB is candidate key, definitely it is super key. So yes, it is satisfying the property. Is D super key? Is D, see DB is candidate key, right? So how alone D can be super key? And if you still want to find out, then you can find out the attribute closure of D. Attribute closure of D have we already discussed. It is only DA, not containing all the attributes, so D cannot be super key. We have already discussed, right? So now this is violating the property of BCNF because left hand side is not super key. Now check for third NF. If this is in BCNF, then definitely this functional dependency will satisfy the rule of third NF, right? It is not a transitive dependency, right? Because obviously for BCNF, that relation should be in 3NF. And if this functional dependency is satisfying the property of BCNF, then by default you can say that it is in 3NF, right? If you still want to check, you can check out. I will check out for this one only. D determines A. Is it transitive dependency? Because 3NF, in 3NF we deal with transitive dependency. So what is transitive dependency? This one. How you will check? Either left hand side is super key or right hand side is prime attribute. Then you can say that that is in third NF. That is satisfying the rules of third NF. Left hand side is super key? No. So we have checked for one condition, but check out for second. Is this one right hand side prime attribute? Yes, A is prime attribute, right? So this is satisfying the property of 3NF, the rules of 3NF. This is not a transitive dependency. In another term, you can say what is transitive dependency? Non-prime attribute determining non-prime attribute. But this is what? A prime attribute, not a non-prime attribute, right? So it is in 3NF, but it is not in BCNF. So definitely it would be in second NF, and highest normal form of this relation is 3NF. And you will find a rare case in which a relation is in 3NF but not in BCNF, because almost every relation which is in 3NF will be in BCNF, right? So this is one of that case when this is in 3NF but not in BCNF. So this is all about BCNF normal form, how to find out that a particular relation is in BCNF or not, right? So we also discuss some practice questions like this also. We'll take one relation and we'll discuss the highest normal form. We'll find out the highest normal form in that relation, right? Some complicated type of questions in the next video, right? And also we'll take one table, and with help of that table, we'll not take these type of relation, we'll take a proper table with some data, and we'll find out that particular table is in that desirable normal form or not, right? So now I'll see you in the next video. Till then, bye bye, take care.